Solucis is located on the waterfront and features a highly open structure toward the water, symbolizing harmony with its aquatic surroundings. Byakuya wanted to preserve the basic outline of the building site provided by the city and decided to experiment with the two ends of the structure. So, opening out toward the water was chosen, which led to a diagonal opening, and Solucis bordered from rises from the water. This design was made with a massive cantilever. An enormous building constructed on soft ground of water, combined with its unique design and complex load mechanisms, made thorough foundation design and engineering an indispensable task to ensure structural stability. The first step undertaken in the foundation engineering design was the geotechnical investigation. The weeks of soil was thoroughly investigated using the compenetration test to inform the foundation design. Through this geotechnical investigation, the composition of the soil was identified. Until approximately -60 meters below the water surface, there is a soft soil layer and a thin weak first sand layer that is inadequate for supporting piles. Therefore, the actual bearing strata are the second sand layer, which extend from then -60.5 meters to then -25 meters, and the third sand layer starting around then -49 meters. The second sand layer, starting at approximately 60.5 meters below Dutch sea level, has a strength of around 25 megapascal. Soft clay, silt layer were found to extend down from a depth of 25 meters. These layers exhibit very low current resistance, making them unsuitable for supporting structural loads. After the weak layer, the third sand layer, beginning at 49 meters, possesses a strength exceeding 40 megapascal. Due to a weak clay starting between these two sand layers, the piles were strategically placed according to the weaker strengths determined by structural analysis. To support the cantilevered load, Solucis used a structural system in which the slab and shear walls function analogously to the flanges and web of an H-beam. The massive cantilevered wing acts as a single flexural element, transferring significant compressive forces and moments downward through a lower compression strut that serves as a bottom flange. Although the overall load mechanism is not strictly separable in analytical terms, the foundation was practically divided into three functional zones for the sake of design clarity. A compression zone that bears the heavy compressive loads, a mattress zone which broadly distributes loads like a bed mattress, and a tension zone which experiences slight tension as a result of a cantilever's structural behavior. This segmentation guided the foundation design strategy. Amsterdam has a long-standing tradition of utilizing its canal network, and this was actively applied in the construction of sluices as well. Just like timber for piling was transported into the city via canals during the Dutch Golden Age, the unique waterfront location of sluices was strategically leveraged for the transport of large construction materials and prefabricated boulders by barge. As will be detailed shortly, the foundation of sluices employed 714 precast concrete piles, each approximately 15 to 70 meters in length, and 99 steel tubular piles ranging from 55 to 57 meters. Due to their large size, these piles could not be transported over land and were instead manufactured at a factory in Friesland, the Netherlands, and delivered to the site by barge. The precast concrete piles were fully fabricated in the factory and installed on-site without the need for any additional assembly, significantly reducing on-site casting operations. The large diameter steel tubular piles were manufactured in segments and also transported via barge. These segments were then welded together on-site to form continuous piles, which were lifted vertically and installed into the ground using crane system mounted on barges. Prefabricated elements produced in the factory reduce construction tolerance, ensure guaranteed strength, and facilitated pile installation in complex site conditions. Located at both ends of the L-shaped underground structure, the compression joints were designed to resist a total load demand of 285,000 kN. Each joint is supported by 48 screw-tip steel tubular piles. These piles have an outer diameter of 990 mm and an inner diameter of 864 mm. After being positioned into the ground, they are filled with reinforced concrete to bear high concentrated loads ranging from 6,000 to 10,000 kN per pile. The piles in the compression zones are embedded in the third sand layer to prevent settlement and ensure stable bearing capacity at depths ranging from depth minus 59.5 meter to minus 62.5 meter. They are arranged in a grid pattern with horizontal spacing of 2.1 meters and vertical spacing of 1.5 meters, forming a layout of 12 by 4 grids per compression zone. The foundation transmits approximately 1,500 kN per meter square of load to the ground surface. While this bellow remains within the strength capacity of the third sand layer, the design included additional measures to ensure safety. The base area in contact with the soil was enlarged and the piles were inclined at a 21 ratio to more effectively carry the load transmitted through the sloped compression struts. The piles used in the compression zones of sluices were installed using the 2-box method, a Dutch-developed vibration-free rotary insertion piling technique. In this method, a thin steel casing with a screw-pointed drill tape is rotated into the ground and subsequently filled with reinforced concrete. Construction begins by assembling the steel casing onto a pre-positioned screw tip at the ground surface. Unlike traditional impact-driven piles, these are inserted using rotary drilling equipment. The piles are advanced into the ground using a soil displacing method, which pushes soil laterally rather than excavating it. This technique not only avoids disturbing the surrounding ground, but also compacts the adjacent soil, effectively increasing its bearing capacity. One of the key technique features of this method is the grout smear technique. As the pile reaches dense sand or compacted sandy soil, where penetration resistance increases significantly, grout is pressure injected around the exterior of the steel casing. This artificially reduced shaft friction, elevates stress on the drilling equipment, and prevents damage to the steel surface. The grout forms a thin layer between the steel and the soil, functioning similarly to the enlarged pile diameter and enhancing load-bearing performance. Once the pile reaches the designated depths, a reinforcement cage is inserted and high-strength concrete is poured into the steel casing. The combined use of steel and concrete allows the pile to take full advantage of both materials. The steel resists buckling and handles tensile forces, while the concrete provides high compressive capacity and ductility. This results in an efficient composite element capable of withstanding significant axial and lateral loads. However, this method presents certain technical challenges. For instance, as the concrete cures, shrinkage may create micro voids between the steel wall and the concrete core, weakening the bond and potentially distorting stress transfer or causing cracks. To mitigate these issues, several strategies were implemented during design and construction. Self-compacting concrete with high flow ability was used to ensure uniform filing without voids. Vibration or vacuum assist method were applied to further enhance compaction. Additionally, the inner surface of the steel casing was roughened or sandblasted to improve the mechanical bond, between steel and concrete, ensuring that the pile behaves as a unified structural element. Since the piles in the compression zone were installed at significant depths, strict measures were taken to prepare for any potential deviations during the construction process. A system was established on site to analyze the drilling process and immediately verify any deviations during pile installation. Through this system, issues that arose during construction could be identified and addressed in real time. During the installation of compression zone piles, certain soil layers exhibited much higher resistance than anticipated, requiring particularly careful execution. For example, during the installation of pile 524 and pile 526, drilling operations had to be halted at net 54 meter and net 49 meter, respectively, due to excessive resistance. In this case, the surrounding high-pressure soils were cleaned during the piles were partially extracted to net 32 meter, and then the piles were successfully installed to the target depth in a single operation. While some piles were successfully installed despite the high resistance, others failed. For instance, during the installation of pile 557, drilling was stopped at net 46 meter when it was discovered that the layer consists of soft clay with high resistance but insufficient bearing capacity. So the pile was subsequently extracted. Similarly, forced to pot piles in the lower compression zone of Suez encountered excessively high soil resistance during installation and could not reach their design depths. Consequently, a working platform was installed above these piles, and additional geotechnical investigations were carried out to verify if they could still achieve the required bearing capacity. Cone penetration tests confirmed that although the piles had encountered high resistance due to friction, the bearing layer itself was weak clay with inadequate strength. Based on the geotechnical reassessment, concerns arose that the problematic piles might reduce the foundation's overall bearing capacity and increase sediment risks. Therefore, 3 additional large diameter steel piles with an internal diameter of 940 mm and an internal diameter of 1050 mm were installed down to net 62.5 meter to compensate. However, additional challenges were encountered during the installation of the supplementary piles. Initially, the plan was to install reinforcement piles near pile 502 and pile 560. Yet, during drilling, extremely high cone resistance values of approximately 70.5 megapascal and pressures of around 20 tons were recorded at 51.6 meter and 50 meter depths, respectively. Although these values exceeded the required bearing capacity according to the design criteria, the resistance was so great that it was impossible to reach the target depths. Given the Suez was subject to significant loads, moments, and subsequent conditions, its settlement behavior had been meticulously calculated. Uneven pile depths could cause differential settlement, leading to torsional forces and additional stresses in the foundation and structure. Thus, achieving uniform pile depths was critical. As a result, the reinforcement locations were reassessed, and 3 additional piles were installed at intermediate points near piles 519 and 489 and 492. In the overall structural system of Suez, the massive cantilever behaves like a large flexural member supported at the compression footing. Consequently, a small amount of tensile force is induced at the ends of the cantilever, forming the tension zones. These zones are located at both far ends of the L-shaped underground structure and are designed to resist a total tensile demand of approximately 10,000 kN, supported by 56 piles per zone. The piles in the tension zones are 400 mm x 400 mm square precast reinforced concrete piles anchored into the second sand layer at depths of 21 to 23 meters. These piles rely on frictional resistance with the soil to counteract the uplift forces. Each pile is subjected to approximately 300 to 400 kN of tensile load, well below the tensile yield strength of concrete. Rather than providing structural stability through direct tensile resistance, these piles primarily function to resist uplift and overturning moments occurring at the cantilever extremis. They are arranged in a 14 by 4 grid with a spacing of 1.4 meters in both directions. The mattress joint functions as a buffer layer that broadly distributes the building's weight. This zone encompasses the remainder of the L-shaped basement area, excluding the compression and tension zones. In this region, the foundation is subject to a distributed load of approximately 100 to 200 kN per square meter. To support this, 602 square precast reinforced concrete piles, identical in dimension in those used in the tension zone, were installed. This is a significantly larger number of piles compared to other buildings of similar scale, chosen specifically to mitigate thermal risk on the weak underlying soil by spreading the load across many contact points. These piles were strategically arranged to match the building's load paths. 4 piles were placed under interior columns, 2 under exterior columns. Each of these piles was designed to bear up to 2,000 kN of load, which the second cell layer can sufficiently support. Accordingly, the piles were fabricated to lengths of 21 to 23 meters. The precast concrete piles used in the tension and mattress joints of sluices were installed using an impact-driven method. This method involves lifting the heavy precast piles into a vertical position and driving them into the ground through repeated hammering. The precast piles were factory fabricated to ensure consistent quality and are transported to the site via barge. Once on site, barge-mounted cranes position the piles precisely at their designated locations. To minimize position errors, the installation relied on GNSS-based positioning systems and precision surveying instruments, ensuring accurate placement within tight tolerance. To facilitate penetration into the soil, the leading end of each precast pile was equipped with a steel tip. As piles were driven into the ground, records were kept of hammer blow counts and penetration depths, allowing engineers to verify in real time whether the record embedment depths and bearing capacity have been achieved according to the structural design. Additionally, to prevent vertical deviation or tilting during installation, alignment guardian systems such as horizontal guide frames were used to ensure the piles remaining plumb throughout the driving process. Next week, we plan to cover the underground construction process of sluices. Topics will include the installation of the cofferdam to create a dry working environment, the casting of footings and med slabs to connect the piles with the structural elements, and the construction methods for the underground structure based on the load, mechanisms, and the waterfront conditions.